Earth is not the only world with rings. Far beyond Neptune, a distant dwarf planet named Quaoar carries something astronomy still struggles to explain. Its rings orbit so far away that they should have collapsed into a moon long ago. But they did not. Tonight. This journey follows one of the strangest discoveries in the outer solar system, and the quiet mystery of why these impossible rings still exist. If this kind of deep space mystery belongs on the channel, please like the video, subscribe, and stay with the story. Far beyond the bright central region of the solar system, past the paths of the giant planets, the Sun still holds a wide, cold population of distant bodies in orbit. This region is the Kuiper Belt, a broad disk of icy objects beyond Neptune. It is not a thin line and not an empty margin. It is leftover material from the era of planet formation, spread across great distances and moving slowly through weak sunlight. NASA describes the Kuiper Belt as a donut-shaped or disc-shaped region beyond Neptune, extending roughly from 30 to 55 astronomical units from the Sun, and containing vast numbers of icy bodies, including dwarf planets and the source region of many short-period comets. In this outer belt, Quaoar belongs to a population known as trans-Neptunian objects, meaning bodies that orbit the Sun beyond Neptune. The phrase sounds technical, yet its meaning is simple. These are solar system members that remain in the far outer dark, where sunlight is faint and seasons unfold on timescales far longer than a human life. NASA and standard astronomical references describe this zone as the third great region of the solar system, after the rocky inner planets and the giant planets, and they treat its inhabitants as preserved remnants of early solar system history. The setting is quiet, though not motionless. Every body in the Kuiper Belt continues along its own path around the Sun. The belt is populated, but it is thinly populated in terms of local spacing. Individual objects are separated by immense reaches of empty space. Seen from within, the region would not resemble a crowded ring of stones. It would feel open and sparse, with one icy world after another placed far away from the next. This sparseness matters because the Kuiper Belt is shaped less by constant contact and more by long-term orbital order, by the history of migration among the giant planets, and by the lingering structure left behind when the solar system settles into its present arrangement. Modern reviews of outer solar system small bodies describe Kuiper Belt objects as among the most pristine leftovers from the solar system's formation, preserving clues to the early protoplanetary environment. The Sun governs this region with the same gravity that holds Earth, Mars, and Neptune, yet distance changes the character of that rule. At the Kuiper Belt, solar energy is greatly reduced. Light still arrives, but warmth is slight. Surface temperatures on bodies in this realm remain extremely low, allowing volatile materials such as water ice, methane ice, nitrogen ice, and other frozen compounds to persist far more easily than they can in the inner solar system. That is why many Kuiper Belt objects are described as icy rather than rocky, even though rock is present as well. They are mixed bodies, built from frozen materials and darker mineral matter, but the outward setting strongly favours the survival of ice. NASA's overviews of Kuiper Belt objects and trans-Neptunian bodies emphasize that these distant worlds preserve ices and primitive material from the early solar system. This outer belt also carries a historical meaning. It is not only a place where objects happen to reside at present, it is a surviving record of a much older solar system, one that is still forming planets, shifting giant worlds, and redistributing countless small bodies. The major planets consume, scatter, and reshape much of the original material close to the Sun. Farther out, the process remains incomplete. Bodies endure there that are large enough to become worlds in their own right, but too small and too isolated to dominate the region the way a major planet does. Quaoar is one of these surviving bodies. It is not alone in that status. Pluto, Haumea, Make, and Eris are part of the same broad family of distant icy worlds, and together they show that the outer solar system does not fade into simplicity beyond Neptune. NASA notes that the Kuiper Belt is home to Pluto and most of the known dwarf planets, underscoring that this remote zone contains substantial worlds rather than only debris. The geometry of the Kuiper Belt is also important. The region is broadly flattened, following the general plane in which the planets orbit, yet it is not perfectly smooth. Some objects travel in more tilted paths, some occupy resonant paths linked to Neptune, and some move on more elongated orbits. This means the Kuiper Belt is not one simple band with a single pattern of motion. It is a layered dynamical landscape. Standard references describe it as a flat or flattened region beyond Neptune, but observations also reveal a variety of orbital classes within it. Quaoar lives within that wider structure, and its place in the belt is therefore both ordinary and special. It is ordinary because it is one member of a trans-Neptunian population. It is special because it is large enough to preserve a world-like identity inside that population. Distance changes time in subtle ways here. A body in the Kuiper Belt requires centuries to complete one trip around the Sun. Change is real, but it proceeds gently. Illumination shifts with the slow rhythm of a long orbit. Surface frost patterns may alter over immense intervals. Collisions can occur, but not with the frequent violence imagined for denser regions of the young solar system. The present belt is more like a faint memory of that earlier era, still carrying bodies that bear scars of formation and rearrangement, yet doing so in a quieter state. Because of this slow pace, the Kuiper Belt often appears less like an active frontier and more like a cold archive. Astronomers treat it as a reservoir of ancient material because its distance helps preserve what the warmer inner system tends to erase. Even at this broad scale, Quaoar takes on its proper setting. It is not an isolated oddity floating in a blank outer void. It resides in a distant planetary borderland filled with frozen bodies, ancient debris, dwarf planets, and long orbital histories. Its environment is cold, weakly lit, and dynamically ordered over immense spans of time. The background to its story is therefore not one of chaos, but of restraint. Matter endures, motion is steady, the sun is small in the sky. The surrounding population is sparse yet significant, and the entire region preserves the outermost surviving architecture of planetary formation in that setting. Quaoar is first understood as a member of the Kuiper Belt, a large icy remnant orbiting in one of the oldest and quietest regions of the solar system. At Quaoar's distance, sunlight remains present but greatly diminished. The sun still governs day and season, still casts light across exposed ice and darker ground, and still sets the thermal balance of the world, yet it does so from very far away. The Kuiper Belt begins beyond Neptune and extends across a broad outer region of the solar system, and trans-Neptunian objects in that region receive only a small fraction of the energy that reaches Earth. NASA describes these bodies as very cold, and recent web material notes that trans-Neptunian objects are commonly below -170 degrees Celsius. In such a setting, warmth is weak, sparse, and slow to change. The weakness of sunlight follows a simple physical rule. As distance from the sun increases, the same solar power spreads across a larger and larger area. By the time light reaches the Kuiper Belt, it is diluted across vast space. The brightness of day there is therefore faint compared with the inner solar system. and the amount of energy available to heat a surface is correspondingly small. A body in this region does not quickly warm in daylight and does not hold a large daily surplus of heat. Its surface settles into a long cold equilibrium, meaning a balance between the sunlight it absorbs and the energy it radiates away as invisible infrared light. That balance lies at very low temperatures because the incoming energy is so limited. In this outer environment, cold is not just a background condition. It becomes one of the main facts that shapes matter itself. Materials that are rare or fleeting closer to the sun can remain frozen here for immense spans of time. Water ice is stable, and more volatile substances, meaning substances that vaporize more easily, can also survive at the surface or just beneath it depending on local conditions. The result is a landscape and a population of objects in which ice is ordinary rather than exceptional. This is why NASA consistently describes Kuiper Belt objects as icy bodies and as remnants that preserve primitive outer solar system material. Cold also changes the pace of surface change. In warmer regions, heat drives more active cycles of melting, evaporation, and chemical alteration. At Quaoar's distance, those forms of change are severely reduced. There is no liquid water operating at the surface, and the exchange between solid ice and gas is far slower and more restricted than on worlds that lie nearer the sun. Even when a volatile ice is capable of turning directly into gas, that process tends to remain limited by the severe cold and the weak solar input. A surface in this region can therefore preserve ancient textures, ancient coatings of frost, and long-lived mixtures of bright and dark material. Observations of trans-Neptunian objects often treat them as valuable records, partly for this reason: their cold surfaces erase history more slowly. The thermal setting is also remarkably slow in time. Near the sun, daily heating and cooling can produce sharp contrasts. In the far outer solar system, the input is so weak that changes proceed with less urgency. A sunlit surface still warms relative to shadow, but the overall range remains within a deeply frozen domain. Heat penetrates shallowly, then leaks back out gradually. This helps create a world where surface layers may remain cold enough for frost to persist, while deeper layers respond only over long intervals. Such slow thermal behavior matters because it governs how easily grains separate, how frost forms on exposed material, and how strongly an icy crust resists disturbance. Under these conditions, ice behaves less like familiar snow and more like a hard mineral. At very low temperatures, many ices become rigid and brittle, and their surfaces can acquire coatings of frost that alter how grains touch one another. A collision between small icy pieces in such an environment is not automatically a simple act of sticking together. Planetary scientists studying Quaoar's rings have pointed to the possibility that extremely cold, frost-covered particles may collide in a relatively gentle or elastic way, reducing the efficiency of growth into larger bodies. The important point at this stage is broader than the ring itself. Extreme cold changes contact physics. It affects whether grains compact, rebound, fracture, or remain separate after meeting. This same cold reaches into the chemistry of the surface. Sunlight that is too weak to warm strongly is still strong enough over long periods to alter exposed molecules. Radiation from space, together with faint solar energy, can gradually process surface ices and organic compounds, darkening some regions and changing how the ground reflects light. Yet these changes unfold on top of the deeper fact of preservation. The materials remain cold, and many of them remain frozen. They are not chemically motionless, but their chemistry advances under conditions of extreme refrigeration. For Quaoar, the thermal setting acts as both a conservator and a slow modifier. holding ancient material in place while allowing only subtle alteration at the surface. Because the sun is weak here, even a small difference in reflectivity can matter. A bright patch reflects more light and tends to stay cooler. A darker patch absorbs more and may warm slightly more during illumination. Over long periods, these small differences can help separate terrains by texture, frost cover, and thermal response. The surface does not become warm in any ordinary sense, but it does become uneven in how it handles the little energy it receives. This is another reason the outer solar system does not consist of simple, uniform ice bodies. Even in deep cold, local variations still matter. Taken as a whole, the thermal world around Quaoar is one of restraint. Light arrives after a long passage across space and delivers only a faint share of the sun's power. Surfaces remain far below the freezing point of water. Volatile substances can endure, and the pace of change slows almost to stillness. In that environment, ice is stable, heat is shallow, and collisions among cold grains may follow rules that differ from the warmer inner solar system. Nothing in this setting acts quickly. Cold sets the tempo, sunlight sets the limit, and matter responds with patience. Quaoar exists within that deep outer refrigeration, where weak illumination and enduring frost create the quiet physical background against which its local mysteries must first be understood. Quaoar moves around the sun on a path that is long, measured, and comparatively regular for so distant a body. It does not race inward and outward across the outer solar system in a strongly stretched ellipse. Instead, it follows a nearly circular orbit at an average distance of about 43.7 astronomical units. An astronomical unit is the average distance between Earth and the Sun, and at more than 43 of those units, Quaoar remains deep in the Kuiper Belt throughout its journey. Recent work describes it as a hot classical Kuiper Belt object with a semi-major axis near 43.7 astronomical units and an orbital inclination of about 8 degrees. NASA's older Hubble description also notes that its orbit is notably circular compared with many other distant bodies. That broad solar path takes a very long time to complete. Quaoar needs roughly 289 years for one revolution around the Sun. In ordinary human terms, one Quaoar year is longer than the span separating the late 18th century from the present day. This long period is one reason the outer solar system feels less like a scene of rapid motion and more like a system arranged on deep time. Bodies there do not merely move slowly in space, they also move slowly through eras. Quaoar's progress around the Sun is steady enough that changes in its orbital position become meaningful, mainly when considered across generations of observers and long sequences of calculation. Its path varies only modestly in distance. The orbit carries it from a nearest solar distance of a little above 41 astronomical units to a farthest distance of roughly 45 astronomical units. That range is real, but it is not extreme. Quaoar therefore remains within the same broad thermal and dynamical zone of the Kuiper Belt, rather than wandering between very different solar environments. A recent compositional study describes Quaoar as having a nearly circular orbit around 43.7 astronomical units, and notes that this keeps it within the more typical irradiation environment of the Kuiper Belt. In simple terms, the Sun always remains weak there, and the orbital path does not carry the body far enough inward or outward to transform the character of that setting. This near circularity distinguishes Quaoar from some other famous outer solar system bodies. Pluto, for example, follows a more eccentric path and enters a resonant relationship with Neptune, meaning that repeated timing between the two orbits helps maintain long-term order. Quaoar does not belong to that resonant class. It is generally treated instead as a classical Kuiper Belt object. specifically part of the dynamically hot classical population. In this context, hot does not refer to physical temperature. It refers to orbital excitation, especially the fact that the orbit is more inclined and somewhat more stirred than the flatter, calmer orbits of the cold classical group. Studies of Kuiper Belt populations define the cold classicals as low-inclination objects between the main resonances, while the hot population occupies more inclined and dynamically disturbed paths. Quaoar belongs to that stirred class even though its orbit around the Sun remains fairly round. Its inclination matters because it adds a vertical element to the path. Quaoar does not remain exactly in the shared flat plane followed by the major planets. Instead, its orbit tilts by about 8 degrees relative to that reference plane. This is not a dramatic tilt by the standards of the outer solar system, but it is enough to separate Quaoar from the especially calm classical objects whose orbits lie closer to the plane. That modest tilt places Quaoar among bodies whose histories likely include some degree of past gravitational stirring during the early outward migration of Neptune. Modern classifications of trans-Neptunian populations treat higher inclination classical objects as evidence that the outer solar system preserves not only leftover material, but also the record of ancient rearrangement. Quaoar's solar path therefore carries a memory of formation history in its geometry alone. Even so, the orbit is not wild. It stays well beyond Neptune and does not plunge into the giant planet region. That allows Quaoar to remain a long-term resident of the outer belt, rather than a transient visitor from a more unstable reservoir. The important feature here is persistence. Quaoar occupies a solar path that is broad, distant, and durable. It belongs to the architecture of the Kuiper Belt rather than to the more chaotic traffic of short-lived scattering or repeated close planetary encounters. This persistence helps explain why astronomers treat Quaoar as a substantial world of the outer system and not merely as a temporary fragment passing through it. Its orbit defines it as an enduring member of the distant planetary margin. The pace of orbital motion in such a path is also gentle. Average speed around the Sun remains far lower than the orbital speed of the inner planets, because gravity weakens with distance and the orbital circumference becomes immense. Yet slow does not mean simple. Over centuries, the path traces a precise balance between solar gravity, the inherited conditions of solar system formation, and the long-settled arrangement of the giant planets. Every point along the orbit is part of that balance. Quaoar advances, the Sun remains distant, and the geometry of the path keeps the body within a narrow band of outer solar system conditions. The orbit is therefore less a dramatic ellipse than a quiet rule that repeats across centuries. Its solar path also determines what kind of sunlight and radiation environment it receives over time, because the orbit stays within a relatively limited range of distances. Quaoar experiences a comparatively stable outer belt regime of weak sunlight, deep cold, and long-term surface irradiation. That stability matters for interpreting its surface materials, because those materials do not cycle through strongly different solar distances the way more eccentric bodies can. Observations and modelling therefore treat Quaoar as an object that remains embedded in a familiar Kuiper Belt environment over long spans, rather than one that repeatedly samples sharply different conditions. The orbit shapes not only where Quaoar is, but the continuity of the environment that acts upon it. Seen at the scale of the whole solar system, Quaoar's path is both ordinary and revealing. It is ordinary because many classical trans-Neptunian objects inhabit distant, long-period orbits beyond Neptune. It is revealing because its specific combination of distance, low eccentricity, and moderate inclination places it in a meaningful dynamical class. It occupies the outer solar system not as a scattered exile, not as a resonant companion of Neptune, and not as an inward-crossing wanderer, but as a large member of the hot classical belt. Its journey around the Sun is calm in shape, long in time, and slightly lifted above the common plane. In that orbit, the outer solar system expresses one of its quieter arrangements, a cold world held far from the Sun, circling on a broad path that changes little in character even as it takes centuries to complete. At the scale of its own immediate surroundings, Quaoar is no longer one distant member of a broad outer belt. It becomes the central body of a small and orderly local system. Around it, the known structure is compact and layered. There is Quaoar itself at the centre. Two narrow rings set at distinct distances from that centre, and one confirmed moon travelling still farther out. This arrangement gives the system a clear radial form. It is not a swarm of scattered fragments. It is a nested set of paths around one dominant body, each path separated from the next by measurable empty space. Observations indicate that the architecture is not random. The components occupy specific orbital distances and together define a miniature planetary system in the far outer solar system. Quaoar serves as the anchor of that system because it contains nearly all of the mass involved in the local arrangement. Stellar occultation work gives an area equivalent radius of about 543 kilometers, which means that every other known component can be described in relation to that central scale. The rings are not close skims over the surface, and the moon is not loosely attached to the body itself. Each element lies many Quaoar radii away from the centre, so the system has real extent even though it remains tiny compared with the spacing between separate Kuiper Belt objects. In plain terms, Quaoar rules a local region around itself, and that region is large enough to support distinct orbital zones rather than only one immediate layer of nearby debris. The inner known ring, called Q2R, lies at a distance of about 2,520 kilometers from the center of Quaoar. The outer known ring, called Q1R, lies farther out at about 4,057 kilometers. These distances matter because they show that the system is tiered. There is a first ring zone, then a second and more distant ring zone, and only after that does the space open toward the path of the moon. Q2R therefore marks the first stable ring structure known in the system, while Q1R marks a second and broader orbital tier beyond it. Both rings are centered on Quaoar, and observations indicate that Q2R is consistent with being concentric and coplanar with Q1R, meaning that both rings appear to share the same central alignment and the same broad orbital plane. That shared plane is one of the most important features of the local architecture. In planetary systems, a plane is the flat geometric surface in which orbits lie. It is not always exact in practice, but it provides the basic shape of the system. For Quaoar, the published occultation analysis indicates that the orientation of the outer ring is consistent with Weiwot and Q1R, orbiting in Quaoar's equatorial plane, and the inner ring is also treated as coplanar with that arrangement. This gives the local system a quiet geometric unity. Rather than separate components crossing at different angles, the known pieces appear to form a flattened family around the body's middle region. Such alignment is what gives the system its sense of order. Each component circles the same center and, so far as observations show, does so within nearly the same broad orbital sheet. Beyond the rings lies Weiwot, the one confirmed moon of Quaoar. Earlier orbital work places Weiwot on a path with a period close to 12.4 days and a semi-major axis near 14,500 kilometers, while recent studies indicate that its orbit is less eccentric than once thought and remains an important guide to the structure of the overall system. For the present local view, the main fact is positional. Weiwot orbits well beyond both known rings. It does not sit between them, and it does not travel just outside the outer ring. It belongs to a clearly separate outer tier of the system. This spacing creates a simple sequence from center to edge Quaoar, then Q2R, then Q1R, then Quaoar. The system is therefore easy to describe in radial terms, even though the physical behavior within each tier is more subtle. The ring system itself is not made of two identical bands. Q2R appears relatively narrow and tenuous, while Q1R shows a more complex spread in width and density. Yet at the scale of architecture, both remain recognizably ring-like and remain separate from the Moon's path. Q2R occupies the closer ring zone with a typical width near 10 kilometers. Q1R occupies the outer ring zone and is much less uniform, with reported widths that vary from only a few kilometers in dense segments to much broader portions elsewhere. Even without entering the detailed physics of that structure, the distinction already matters. The local system is not composed of one smooth belt. It contains an inner ring and an outer ring that differ in appearance and extent while remaining part of the same organized framework around Quaoar. Seen as a whole, the Quaoar system is compact when compared with the great scales of planetary orbits around the Sun, but internally it is spacious. Between the surface of Quaoar and the inner ring there is a wide gap. Between the inner ring and the outer ring there is another substantial interval. Beyond the outer ring, the space out to Quaoar is larger still. This layered emptiness is just as important as the material itself, because a system is defined not only by what it contains, but by how those contents are separated. The result is a clean radial design in which each known component occupies its own orbital domain. Nothing in the observed layout suggests a confused or cluttered environment. The structure appears sparse, flattened, and strongly centered on the main body. In this local frame, Quaoar is best understood not as a lone distant world, but as the center of a ring-moon system with distinct orbital levels. The central body gives the system its scale. The two rings define the inner and middle orbital layers. Quaoar defines the outer confirmed layer. Observations indicate that these components are arranged in a common broad plane and occupy specific, persistent distances from the center. That is the basic architecture from which the mystery of Quaoar's rings begins to take shape. Before any attention turns to how the rings are detected, why they occupy these distances, or what keeps them from changing form, the system first stands as a clear physical arrangement, one icy dwarf planet in the Kuiper Belt, circled by two narrow rings and one confirmed moon, all ordered around a common center in the deep outer dark. Quaoar's rings do not first appear as visible bands in a direct image. At that distance, imaging does not easily show such fine structure. The rings emerge instead through a different method, one built from timing, alignment, and the behavior of starlight. Astronomers watch Quaoar pass in front of a distant star. This event is called a stellar occultation. During it, the background star briefly dims or disappears because Quaoar moves across the line of sight. The method is simple in principle, but exact in practice. It depends on a very precise alignment between the distant star, the moving body in the outer solar system, and the telescope that records the event. When such an alignment occurs, the star acts like a backlight. Quaoar itself is too small and too distant for many of its fine properties to be measured directly in ordinary ways, but the temporary loss of starlight allows astronomers to infer shape, size, and surrounding material from the pattern of the fading light. Issa explains that the drop in the occulted star's light provides information about the occulting object's size and shape, and can reveal whether the intervening object has an atmosphere. In Quaoar's case, The same method reveals small additional drops in brightness before and after the main passage of the body itself. Those brief dimmings are the signature that leads to the rings. A light curve is the record of how brightness changes over time. For an occultation, it shows when the star remains steady, when it suddenly falls, how long it stays faint, and when it returns. If only Quaoar crosses the star, the central feature reflects the body's own passage. But if material circles Quaoar at some distance from the centre, the star can dim earlier and brighten again before the main body arrives, then repeat a matching pattern after the body has passed. In a ring system, those extra events are small, brief, and easy to miss unless the measurements are fast and clean. The discovery of Quaoar's rings therefore depends on a sequence of subtler dips arranged around the main occultation. That observational strategy unfolds over several years. The outer ring, Q1R, is identified from stellar occultations observed between 2018 and 2021. The later two-ring analysis reports that this first ring is detected during several such events, and that the pattern is consistent enough across them to establish a real structure in orbit around Quaoar, rather than a one-time accident in the data. Repetition matters greatly in occultation work. A single unexplained dip could arise from noise, atmospheric disturbance, or instrumental limits. A recurring dip at the correct geometry across separate events carries much more weight. Quaoar's ring system becomes convincing because the observations accumulate and agree. Ground-based telescopes play a major role in this process, because the shadow path of an occultation falls across only certain regions of Earth. Astronomers organize observations from different sites in order to increase the chance that the event is caught and to record it from more than one location. ESA notes that a collection of ground-based telescopes follows Quaoar as it crosses in front of a succession of distant stars between 2018 and 2021. These multiple stations do more than improve coverage. They also provide separate light curves through different columns of Earth's atmosphere, with different instruments and timing systems. Agreement among them helps distinguish a true celestial event from a local observational artifact. Space-based observation adds another layer of confidence. ESA's KOPS mission contributes decisive data because it observes above the lower atmosphere. Where Earth-based viewing is troubled by air motion and scintillation, ESA states that the strong signal-to-noise ratio of KOPS proves especially useful and helps rule out the possibility that the brief secondary drops are caused by spurious atmospheric effects. This space-based record offers a cleaner measure of the star's fading and recovery. When that cleaner record matches the pattern hinted at from the ground, the case for orbiting material becomes much harder to dismiss. Prediction is also central to the method. An occultation by a distant trans-Neptunian object can be observed only if the time and path of the event are known with great precision. ESA explains that this has become more successful in recent years because Gaia greatly improves the positions of background stars, allowing the Lucky Star project and related efforts to forecast where and when these rare alignments will occur. This improvement in star maps changes occultation science from a hopeful watch into a disciplined measurement. Quaoar's rings are found because the geometry of the event is predicted carefully enough for telescopes on Earth and in space to be pointed at the correct place at the correct moment. The later occultation observed in August 2022 sharpens the picture further. The analysis reports 9 effective chords across Quaoar. In occultation work, a chord is one path traced across the body's silhouette by one observing line of sight. Multiple chords allow the body's apparent outline to be reconstructed more reliably. The same event also yields additional secondary detections consistent with another ring, Q2R, closer to Quaoar than Q1R. This strengthens the method. The same backlighting technique that first reveals one ring then exposes more complexity when the event is measured with sufficient precision and from enough vantage points. What makes this mode of discovery exact is that the rings reveal themselves only through their effect on light. They are not first seen as bright structures like Saturns in familiar telescopic images. They remain inferred bands of material, traced through timings of dimming measured to fractions of a second. The evidence comes from when the star fades. How deep the fade is, how long it lasts, and whether matching events occur before and after the main occultation in ways consistent with the circular orbit around Quaoar. This is why the language of occultation science is so precise. It relies on geometry, timing, and repetition. By this method, starlight becomes a measuring tool. A distant star briefly illuminates the system from behind. Quaoar passes across that beam. The rings pass across it as well. Each passage leaves a small, ordered mark in the record of brightness. From those marks, astronomers recover a hidden structure in the outer solar system. The occulted star provides a fine temporary line against which unseen matter declares its presence. Quaoar's rings are therefore found not by looking at them in the ordinary sense, but by watching how they interrupt the light of something much farther away, and by reading those interruptions with enough care to turn brief darkness into a map of orbiting material. The outer ring of Quaoar, known as Q1R, occupies the most prominent ring zone in the system, and remains the clearest ring structure yet identified around the dwarf planet. It circles at a distance of a little more than 4,000 kilometers from Quaoar's center, far outside the body itself and well beyond the smaller inner ring. At this radius, Q1R defines the main visible architecture of the local system when that system is reconstructed from occultation data. It is the ring that first draws sustained attention because it is the strongest and most persistent ring signature in the measurements. In the radial layout around Quaoar, Q1R is the broad middle tier between the inner ring and the distant orbit of Quaoar. It is not a faint blur attached to the edge of the body. It is a distinct orbiting structure with its own scale, position, and internal pattern. What first appears simple becomes less uniform when the data are studied closely. Q1R is not best described as one perfectly even circular band with the same brightness and thickness at every point. Observations indicate variation along the ring, both in how much starlight it blocks and in how wide the ring seems to be during different occultation crossings. Some portions appear relatively narrow and concentrated. Other portions appear broader or more diffuse. This means the ring is not built like a continuous solid collar. It is better understood as a ring with changing density around its circumference, where some orbital longitudes contain more concentrated material than others, even at the level of observation alone. Q1R already resists the neat image that the word ring can suggest. The narrowest measurements imply segments only a few kilometers wide, while broader parts extend much farther across. This spread in apparent width matters because it shows that the outer ring cannot be reduced to a single number without losing much of its character. A narrow, dense section and a wider, thinner section may both belong to the same ring, yet they do not behave optically in the same way when they pass in front of a distant star. One produces a sharper and often deeper dip in light. The other produces a more extended or softer event. From these differences, astronomers infer that the material in Q1R is not spread evenly around the orbit. The ring contains structure within structure, a larger band made of smaller variations in crowding and thickness. In this sense, Q1R often appears closer to a system of arcs and dense strands than to a perfectly smooth planetary ring. An arc is a partial concentration along a ring rather than a uniform full circle of equal density. The ring still circles the body, but the material is not shared equally around the whole path. Some regions are stronger and more sharply defined, and others are more tenuous. Observations indicate that Q1R contains such denser portions, and this is one reason its appearance in occultation records changes from event to event. A telescope does not sample the whole ring at once. It samples only the small track cut by a background star's line of sight through the ring at that moment. If the star passes behind a denser arc, the signal is stronger. If it passes through a more diffuse region, the signal changes accordingly. This patchiness gives Q1R a quiet complexity. The ring is stable enough to be detected repeatedly, yet irregular enough that no single occultation provides its full character. One event may capture a narrow, sharp feature. Another may reveal a broader and weaker one. Together, these observations suggest a ring that is present as a real orbiting system, but internally uneven. Its identity does not depend on perfect smoothness. Instead, its identity comes from repetition at the same distance from Quaoar, within the same orbital plane, across multiple observing campaigns. The pattern remains coherent even though the distribution of material within the ring is not uniform. The amount of starlight blocked by Q1R also varies, and this gives further insight into its texture. When a ring is denser, more particles cross the line of sight, and the star dims more strongly. When the ring is thinner or more porous, less light is lost. In a ring of icy particles, the exact drop depends on how closely the grains are packed, how thick the ring is along the viewing direction, and how the particles are distributed within the band. Q1R shows that these properties change around the orbit. It is not merely that one part is wider than another. The ring also differs in how opaque it appears. Some segments seem capable of producing strong, clean dips in starlight, while others are weaker and less concentrated. Even the idea of a single ring plane becomes more vivid when considered through Q1R. The ring appears centered on Quaoar and broadly aligned with the equatorial plane of the dwarf planet. Yet what lies within that plane is not uniform matter spread like paint along a circle. It is a selective arrangement of grains and clumps, orbiting in the same broad sheet but not gathered everywhere in the same way. This is one reason the outer ring feels both simple and elusive. Its orbit is clear. Its internal organization is not. The ring has a definite home in space, but the material within that home is distributed unevenly. Because Q1R lies well inside the orbit of Quaoar and well outside the inner ring, it also occupies a physically isolated zone of the local system. There is empty space on both sides. This helps preserve its identity as its own orbital layer. The ring is not just an extension of the inner ring, and it is not part of the Moon's orbit. It belongs to its own region. That separation makes the irregularity of its structure more striking. Within an otherwise sparse and orderly layout, Q1R carries the richest visible complexity. The system as a whole looks clean and tiered, but the outer ring itself is textured and uneven. Its prominence in the data also makes it the primary observational face of Quaoar's ring system. The first clear signs of rings around Quaoar come from the repeated detection of this outer structure. The later recognition of the inner ring adds depth to the system, but Q1R remains the feature that establishes the ringed nature of Quaoar most forcefully. It is therefore both a local object and an observational landmark. When astronomers speak of the surprising ring around Quaoar, they are usually speaking first of Q1R. Taken by itself, the outer ring is a measured orbit of icy material that does not distribute itself evenly around that orbit. It circles steadily, appears in repeated occultation records, and reveals narrow, dense segments as well as broader, diffuse ones. It forms the dominant ring layer of the Quaoar system and gives that system much of its visible character. Within the quiet cold around the dwarf planet, Quaoar is not a smooth band but a structured ring, one whose patchy concentration of material turns a simple circular path into a more delicate and intricate pattern of orbiting matter. Closer to Quaoar than the prominent outer ring, a second and subtler band of orbiting material appears in the same flattened local system. This inner ring is known as Q2R. It lies at a distance of about 2,520 kilometers from the center of Quaoar, well outside the body itself but clearly inside the orbital zone of the outer ring. In the local architecture, it forms the first ring layer beyond the dwarf planet. Its position gives the system a more intricate structure than a single isolated band could provide. There's not only one ring set around Quaoar, but a second one nearer the center, occupying its own distinct orbital path and confirming that the space around the body is divided into more than one narrow zone of orbiting matter. Q2R does not announce itself with the same strength as Q1R. It is fainter, more difficult to define, and supported by fewer detections. This does not make it unimportant. It makes it delicate in the observational record. The inner ring is not the dominant feature of the Quaoar system. It is the quieter one. Its presence comes from secondary occultation signals that align with a narrow ring closer to the body than Q1R. Because the signal is weaker, the ring is less tightly constrained in detail. Its full extent, local density pattern, and long-term uniformity remain less certain than those of the outer ring. Observations indicate that it is real, but they do not yet describe it with the same confidence or richness. The character of Q2R is therefore shaped by restraint. It appears as a narrow band, with an inferred width of roughly 10 kilometers, and it seems to occupy a comparatively compact orbital lane. This narrowness matters because it gives the ring a defined radial identity. It is not treated as a broad diffuse cloud spread across a large span of space. It is treated as a limited structure, one that occupies a specific distance from Quaoar and does so in a relatively tight way. Even though the measurements are fewer and the signal is weaker, the ring still presents itself as a geometric feature rather than a vague halo. Its closer position also changes the way it belongs to the system. Q2R is the first material band encountered when moving outward from Quaoar into the local orbital environment. There is empty space between the body and the ring, but less empty space than exists between Quaoar and Q1R. This makes the inner ring feel more closely tied to the central world in simple spatial terms. It remains a separate orbiting feature, not attached to the surface and not blending into the outer ring, yet it occupies a more intimate radial layer. In the structure of the system, it acts as the inner boundary of the ring region. Observations further suggest that Q2R is concentric with Q1R and broadly shares the same orbital plane. Concentric means that both rings are centered on Quaoar rather than offset from it. A shared plane means that the system does not appear twisted into different orbital sheets. The inner ring therefore participates in the same overall flattening that characterizes the outer ring and the orbit of Quaoar. This geometric agreement is one of the strongest reasons Q2R fits naturally into the system, rather than appearing as an unrelated or accidental feature. It supports the view that the ring belongs to the same organized environment around Quaoar, even if the physical details of the ring remain only partly known. What is most striking about Q2R is how much it reveals through so little. The ring is not obvious in ordinary images. It does not dominate the observational story. It emerges from careful measurement and from the interpretation of brief, subtle changes in starlight. That modest entrance into the data gives it a different scientific character from the outer ring. Q1R becomes the ring that defines the system in public discussion. Q2R becomes the ring that deepens it. Its existence suggests that the local space around Quaoar is not governed by one single preferred distance for orbiting material, but at least two. That alone adds complexity to the radial layout and to the quiet order of the system. The ring's faintness also implies caution in description. It remains uncertain whether Q2R is as continuous around Quaoar as a classical smooth ring would be, or whether it contains denser sections and weaker sections in the way the outer ring appears to do. The current evidence is sufficient to identify a ring-like structure at that distance, but not sufficient to describe every part of its circumference in detail. In this sense, Q2R lives closer to the threshold between detection and full characterization. It has crossed the first boundary, because it is recognized as part of the system. It has not fully crossed the second, because many of its finer properties are still only lightly constrained. Its narrow width contributes to that uncertainty in a practical way. A narrower ring produces shorter occultation events, and shorter events require especially precise timing and strong signal quality if they are to be resolved cleanly. This makes a faint, narrow ring inherently harder to study than a broader or denser structure. Q2R may therefore appear modest in the data not only because it contains less material, but also because its geometry gives observers less time to sample its effect during each crossing of a background star. The ring is present, but it reveals itself only briefly. Even with these limits, Q2R changes the visual and scientific identity of the Quaoar system. Without it, the system consists of one dominant ring beyond the body and one moon farther out. With it, the inner region gains a more layered form. There is now a first ring zone, then a second ring zone, and only after that the wider space extending toward Quaoar. This makes the whole arrangement more orderly and more delicate at once. Orderly, because the system displays repeated structure in distinct bands. Delicate, because one of those bands is faint enough that its full pattern still lies partly hidden. Taken on its own terms, Q2R is a narrow inner ring, closer to Quaoar than the more conspicuous outer band, and real enough to define a separate orbital level within the system. It is quieter in the data, more tentative in its fine details, and less visually dominant than Q1R. Yet it is essential to the local architecture. It shows that Quaoar is surrounded not by one isolated ring, but by a layered ring system, with a subtle inner band tracing its own steady path through the deep cold around the dwarf planet. A ring system is usually interpreted through one central idea in planetary dynamics, the Roche limit. This limit is the distance from a central body inside which tidal forces are strong enough to prevent a nearby fluid or loosely bound aggregate from holding itself together as a larger object. Tidal force means the difference in gravity across an extended body. The near side feels a slightly stronger pull than the far side, and if the object is weak enough, that difference can pull it apart. In classical ring theory, dense rings are expected to survive close to a planet or minor planet because the central body's differential gravity disrupts the earlier stages of moon formation. Outside that limit, the usual expectation changes. There, self-gravity among the particles should become strong enough for matter to gather, collide, and gradually grow into a satellite. The idea remains foundational because it links a visible structure to a simple balance of forces. A ring is made of many small pieces following nearby orbits. Each piece feels the gravity of the central body, but each also feels the weak attraction of neighbouring particles. Close to the central body, the tidal difference across any growing clump becomes significant. If the clump remains loose, its own gravity is not enough to overcome that stretching effect. The material therefore tends to stay dispersed as orbiting particles rather than consolidating into one larger body. This classical picture explains why the best-known dense rings in the solar system are found close to their parent worlds. The rule does not say that all material inside the limit must become a ring, only that this is the region where ring material can remain ring material without readily assembling into a moon. The Roche limit is not one fixed universal distance. It depends on the size and mass of the central body, and also on the density and internal strength of the orbiting material. For a fluid body with little strength, the classical Roche limit lies farther out than it would for a rigid object. Denser particles can resist tidal disruption more effectively than less dense ones, so the critical distance changes with composition. This means the Roche limit is not a painted line in space that exists independently of matter. It is a calculated boundary tied to assumptions about what the orbiting material is like. In work on Quaoar, the classical Roche limit is commonly estimated at about 1,780 kilometers from the center, when the particles are treated as low-density icy material with a bulk density around 0.4 grams per cubic centimeter. In ordinary language, the limit separates two tendencies. On the inside, tides dominate weak aggregates. On the outside, aggregation becomes easier. Aggregation means that small particles collide and remain together, building progressively larger bodies. If the collisions are not too violent and if the material can lose enough energy, clumps can persist after impact and then continue to grow. Over time, this leads toward a moonlet and eventually toward a moon. This is one reason planetary scientists historically view rings and moons as related outcomes of the same raw material under different gravitational conditions. The same population of icy fragments can remain dispersed close to a central body. Yet farther out, the same kind of material is expected to move toward accretion, meaning gradual growth into something larger and more coherent. This rule helps explain why dense, narrow rings are so often discussed together with nearby moons. In many ring systems, moons help maintain sharp ring edges or confine material into specific lanes. Even so, the broader background assumption remains the Roche picture. Rings are most naturally at home in the region where tides already resist large-scale assembly. Beyond that region, confinement alone is not usually enough to remove the basic expectation that a dense ring of macroscopic particles should begin to collect into larger bodies. In this way, the Roche limit becomes more than a formula. It becomes a conceptual boundary between two kinds of orbital material matter that remains as a ring and matter that tends to become a satellite. The usefulness of the idea comes from its simplicity. It does not require every grain in a ring to be identical, and it does not require a ring to be perfectly smooth. It only requires that the central body's tidal influence be strong enough, on average, to frustrate the long-term survival of loose-growing clumps. A ring inside the limit can still contain temporary concentrations. Particles can still collide, rebound, fragment, and form short-lived clusters. What the classical rule describes is the long-term tendency of the system. Persistent accretion into a stable moon becomes difficult close to the parent body because tides keep undoing the early stages of growth. In that sense, the Roche limit is not a momentary event but a guide to what orbiting matter is able to do over time. For minor planets and dwarf planets, the same reasoning applies even though the bodies are much smaller than Saturn. The scale changes, but the principle does not. If the central object has enough gravity to generate a meaningful tidal gradient across nearby orbiting matter, then there is still a region in which a weak aggregate is classically not expected to consolidate. This is why the discovery of rings around small bodies such as Chariklo and Haumea fits comfortably within standard theory when those rings lie near or inside the relevant Roche distance. The central body need not be giant. It only needs to establish the right balance between tidal disruption and particle self-gravity. Applied to Quaoar as a theoretical frame, the Roche limit defines the standard reference distance by which any ring location is first judged. It provides a classical boundary derived from Quaoar's gravity and from assumptions about cold icy particles. Within that frame, the meaning of a ring is clear. A ring is classically associated with the region where tides prevent easy moon formation. A moon is classically associated with the region where matter can gather and remain gathered. This distinction is the quiet foundation beneath modern discussion of small body rings. It is the old rule that gives orbital distance its theoretical meaning and turns a simple measurement into a test of how matter behaves around a distant world. The difficulty with Quaoar's outer ring begins with a simple comparison of distance against theory. The ring Q1R is measured at about 4,057 kilometers from the center of Quaoar. The classical Roche limit for loosely bound icy material around Quaoar is estimated at about 1,780 kilometers. These two numbers do not nearly coincide. They do not even lie close enough to suggest a small correction. The ring sits more than twice as far out as the classical boundary that is supposed to mark the region where dense rings can survive without turning into moons. In scaled form, the contrast is equally clear. Q1R lies at about 7.4 Quaoar radii, while the classical Roche limit is near 3.2 Quaoar radii. The observation and the rule therefore describe very different orbital zones. That is why the ring becomes so important. It is not merely another distant ring around another small body. Ring systems around small bodies had already been found before Quaoar, but those systems fit more comfortably within the expected framework. Quaoar's outer ring does not. It occupies a region where the standard picture says that small icy particles should not remain for long as a dense narrow ring. Beyond the Roche limit, the usual expectation is that repeated collisions among orbiting fragments should gradually dissipate energy and allow matter to accrete, meaning to gather into larger clumps that survive from one encounter to the next. Over time, those clumps should move toward moon formation. Q1R instead remains observed as a ring. The contradiction is not a subtle matter of interpretation. It is the direct reason the discovery is treated as a challenge to standard ring theory. The force of the contradiction becomes stronger because Q1R is not described as a tenuous, nearly invisible dust veil. It is described as a dense ring. A very thin or ephemeral dust cloud beyond the Roche limit would already invite interest, but a dense ring there is much harder to fit into the classical picture. Dense material is exactly the kind of material expected to collide frequently enough for growth to matter. Each orbit gives particles another opportunity to meet, exchange energy, and build temporary or lasting aggregates. Close to a body, tides can disrupt that process. Far outside the classical limit, those tides are expected to be too weak to keep undoing it. That is why the location of Q1R feels so decisive. It is not only outside the traditional ring zone, it is outside it by a large margin, while still presenting itself as organized ring material. The usual language used by researchers reflects this tension. The Nature Discovery paper states that the detected ring is well outside Quaoar's classical Roche limit, and therefore indicates that this limit does not always determine where ring material can survive. ESA likewise describes the ring as much farther out than the Roche limit, and highlights that this is the intriguing part of the discovery. Those statements matter because they show how the observation is received by the field itself. The problem is not a later overstatement or a popular simplification. It is present in the original scientific framing. Q1r becomes notable because it occupies the very region where a classical dense ring is not supposed to persist. The contradiction also persists after the system is refined by later work. The follow-up two-ring analysis does not remove the problem by shifting Q1r inward toward the Roche distance. Instead, it sharpens the ring radius to about 4,057 kilometers, and again notes that this lies far outside Quaoar's classical Roche limit. The improved measurements make the mismatch clearer rather than weaker. This is important because some apparent contradictions in astronomy fade when better data arrive. In this case, improved geometry does not restore the old rule. It confirms the basic anomaly with greater precision. The ring remains where it is not expected to be. The existence of the second ring, Q2r, deepens the same difficulty. Q2r lies closer to Quaoar than Q1r, at about 2,520 kilometers from the center. But even that distance still falls beyond the same classical Roche limit estimate. This means the problem is not confined to one lone outer structure at one surprising radius. The local ring system as presently known occupies orbital territory beyond the classical limit altogether. Q1r remains the stronger and more famous case, because it lies much farther out and defines the public form of the puzzle. Yet Q2r shows that the anomaly extends inward as well. The system is not a narrow exception at a single distance. It is a ringed environment whose known ring zones both sit outside the standard theoretical boundary. This is the reason the old rule appears to fail here. The Roche limit remains a useful classical guide, but Quaoar demonstrates that it is not by itself sufficient to predict where ring material can or cannot persist. The failure is not that the limit has been measured incorrectly by a small amount. It is that a ring exists far from the distance where the classical logic would place it. If the rule were operating alone in its simplest form, Q1r would be expected to have aggregated into a moon, or into moonlets rather than remaining an uneven dense ring. The continuing observational fact that it has not done so is what forces a change in understanding. Something in the physical behavior of the orbiting material, or the local dynamical environment, must be modifying the classical expectation. The existence of the ring proves that the boundary between rings and moons is not governed by distance alone in the straightforward way once assumed. For that reason, Quaoar's outer ring becomes more than a local curiosity. It becomes a test case for the limits of a widely used conceptual framework. The classical Roche picture still explains much about where rings are usually found. Yet Q1r occupies a region where that picture says a dense ring should not remain stable as a ring. The outer ring's measured distance, its continued identification as a real ring, and the confirmation that it lies far beyond the classical limit together form the core of the mystery. The rule does not vanish, but it ceases to be complete. Quaoar's rings show that the old division between ring zone and moon zone is too simple for at least some icy systems in the far outer solar system. Once the outer ring is recognized as a real structure far beyond the classical Roche limit, attention turns from distance alone to timing and repetition. In orbital dynamics, a resonance is a repeated gravitational pattern that appears when two motions fall into a simple, numerical relation. One body may orbit in such a way that it returns to nearly the same geometric arrangement after a fixed number of turns, while another motion, such as a moon's revolution or the rotation of the central body, also repeats on its own cycle. When those cycles line up again and again, the small gravitational effect of each encounter does not remain random. It accumulates in an orderly way. Over long time spans, that repeated order can shape where material prefers to gather and where it does not. In the Quaoar system, this idea matters because the rings are not merely present. They occupy rather specific distances. A ring that forms a narrow lane or a set of dense arcs does not look like material that is free to drift anywhere it pleases. It looks like material that is being guided, limited, or shepherded by some continuing pattern. Resonances offer one way to understand such order. They do not necessarily create matter from nothing, and they do not by themselves explain every property of a ring, but they can organize existing particles into preferred regions of orbital space. In this sense, resonance is not a substance but a rhythm. It is a way that gravity repeats. The outer ring Q1R appears near a special commensurability, meaning a simple numerical relationship with Quaoar's rotation. The original discovery paper notes that the ring lies close to the 3-to-1 spin-orbit resonance. This means the orbital period of particles in the ring is related in a simple repeating way to the time Quaoar takes to rotate. Such a relation is important because it provides a natural location where repeated gravitational effects tied to the shape and rotation of the central body can act more coherently than they do elsewhere. Even if those effects are individually small, repetition can matter. A weak pull delivered again and again at nearly the same phase does not behave like noise. It behaves like structure. This does not require Quaoar to be a perfectly smooth sphere. On the contrary, resonant effects become more relevant when the central body departs from perfect symmetry. A slightly irregular shape, or a mass distribution that is not perfectly even, causes the gravitational field to vary subtly as the body rotates. Orbiting particles then feel a small periodic forcing. Most locations in orbit average that forcing away over time. A resonant location does not. There, the forcing repeats in step with the orbit often enough to matter. This is why narrow rings and arcs in other systems are so often discussed in relation to resonances. The resonance does not need to be violent. It only needs to persist and to favour one orbital zone over neighbouring zones. In the Quaoar system, resonance is therefore one of the first dynamical tools used to explain why ring material might collect into a limited radial band, rather than smearing smoothly across a wider region. Left to itself, a ring of particles tends to spread. Different particles orbit at slightly different speeds at slightly different distances, and collisions among them redistribute energy and momentum. Over time, that process usually widens the ring. A narrow ring suggests that some opposing influence is helping to maintain its confinement. Confinement means keeping the material restricted to a limited span of orbital distance. A resonance can contribute to such confinement by creating a region where motion remains orderly, and by discouraging long-term residence just outside that region. The outer ring's patchy appearance also fits naturally with the language of resonances. A resonance can help maintain not only a preferred radius, but also non-uniform structure along the ring. If the repeated gravitational influence varies with orbital longitude, or if stable zones exist only in certain parts of the orbit, then matter need not distribute itself equally around the full circumference. Dense arcs can arise where particles linger more effectively, while neighbouring sectors remain thinner. In this way, a resonance can support a symmetry without destroying the ring as a whole. The ring still circles the body, but it does so with an internal geography shaped by repeated timing rather than by uniform spreading. Quaoar, Quaoar's moon, adds another possible source of repeated gravitational order. A moon does not need to pass through the ring to influence it. By orbiting farther out, it can still impose long-term perturbations, meaning small repeated changes in the motions of ring particles. If the timing relation between Quaoar and the ring particles approaches a simple ratio, then another resonance becomes possible. This does not mean that every resonance is equally strong or equally important. It means that the dynamical environment around Quaoar is not built from distance alone. It is built from several clocks operating together the rotation of Quaoar. the orbital motion of the ring particles, and the revolution of Quaoar. Where those clocks repeat in simple patterns, gravity gains a way to organize the system. The appeal of resonant confinement is that it helps explain why a ring can remain at a particular location, even when classical distance arguments alone would suggest a different outcome. Instead of viewing the ring as matter that simply happens to be beyond the Roche limit, the system is viewed as matter occupying a dynamically selected lane. The lane is not selected by chance. It is selected by repeated gravitational timing. In such a picture, the ring survives not because distance ceases to matter, but because other influences become important enough to shape where particles remain concentrated. A resonance therefore modifies the simple boundary implied by the Roche limit. It adds pattern to what would otherwise seem like a forbidden region. Even so, resonance is not a complete answer by itself. A resonance can identify where order may arise, and it can help reduce spreading or support arcs, but it does not guarantee that ring material persists forever. The particles must still remain in orbit, still continue to collide, and still avoid rapid growth into larger bodies. What resonance provides is a framework for confinement. It shows how the orbital architecture can favor a ring at one location more than at another. It explains why the ring has a preferred home in the system rather than drifting into a broad, undifferentiated band. For Quaoar, this is already a meaningful shift in understanding. The mystery begins with the failure of a classical distance rule, but the ring's existence at a specific, repeated, and organized radius directs attention toward the deep regularity of orbital motion. Resonances reveal that a ring's location is not simply a matter of being close or far from the central body. It is also a matter of being in step with the rhythms of the system. Around Quaoar, those rhythms may help confine orbiting particles into narrow lanes and denser arcs, allowing the ring to maintain its distinct form in a place where distance alone would predict it. At the level of individual particles, the mystery of Quaoar's rings becomes a problem of contact. A ring is not a solid band. It is a population of many orbiting pieces that continually approach, strike, separate, and meet again. In warmer settings, repeated collisions among icy fragments are often expected to drain enough motion from the particles for them to stick, settle into clumps, and begin the slow path toward a moon. For Quaoar, the leading explanation shifts attention to the opposite possibility. The ring particles may be so cold that their collisions are more elastic than standard ring models usually assume, allowing them to rebound with enough residual motion to avoid lasting growth into larger bodies. The original Nature Discovery paper states that local collisional simulations, based on laboratory experiments, show that elastic collisions can maintain a ring far from Quaoar rather than letting it accrete into a satellite. An elastic collision is one in which the bodies rebound and retain a relatively large share of their motion after impact. In an inelastic collision, more of that motion is lost to deformation, internal vibrations, or local heating, and the colliding pieces are more likely to remain together or at least move more slowly relative to one another afterward. For ring particles, that difference matters greatly. If post-impact speed remains high enough, one encounter does not easily become the seed of a growing clump. If the speed falls too low, mutual gravity can begin to hold neighboring particles together. The Quaoar problem therefore becomes a contest between rebound and capture. The key suggestion in current work is that deep outer solar system cold shifts that contest toward rebound. The review literature now frames this temperature effect quite clearly. A 2024 review on the origins of ring systems notes that Quaoar's rings should accrete into satellites on timescales as short as a few months under standard assumptions, unless their particles behave differently from the usual picture. The same review states that laboratory experiments with icy particles show a strong temperature dependence in rebound behavior. At about 210 Kelvin, collisions are relatively less elastic, with rebound coefficients below about 0.4, while experiments at about 125 Kelvin show more elastic collisions, with rebound coefficients as high as about 0.7. Quaoar's rings are colder still, at roughly 30 Kelvin, so the review argues that collisions there may be even more elastic than those colder laboratory cases. That argument changes the meaning of cold. Earlier sections treat cold as a broad environmental condition. Here, cold enters the problem as a property of impact itself. At very low temperature, icy surfaces may become harder and less prone to the kind of energy loss that encourages particles to remain attached after impact. A collision in Quaoar's ring is then not simply a meeting of two soft, snow-like grains. It may be more like a brief mechanical rebound between rigid, frost-covered pieces whose structure resists deformation strongly enough to keep their relative motion alive. The University of Oulu summary of the discovery work states this directly in simpler terms, noting that Quaoar's distance from the Sun makes its rings much colder than Saturn's, and that old laboratory measurements already indicated that ice particles become more elastic at lower temperatures. The importance of that idea lies in what happens immediately after impact. Two particles may meet and still fail to grow if their post-collision relative velocity remains above their mutual escape velocity. Escape velocity, in this local sense, is the minimum speed needed for the two pieces to avoid remaining gravitationally bound to one another. The review explains that in the colder collision model, the post-impact relative velocity stays above this mutual escape speed, and accretion is prevented even for particles with quite high densities. In other words, the particles can be ordinary icy solids rather than unrealistically fluffy bodies, and still fail to become a moon if the collision physics remains sufficiently spring-like. This helps explain why the classical Roche argument alone fails for Quaoar. The Roche limit assumes a simple division between a tidal zone, where weak aggregates cannot easily survive, and a more distant zone, where orbiting matter should begin to assemble, but that division is sensitive to how collisions actually behave. If distant icy particles rebound more strongly than the classical assumption allows, then the outer region does not automatically become an efficient nursery for moon formation. Matter can remain dispersed longer, not because gravity disappears, but because each collision fails to remove enough motion for the particles to stay bound together. The Nature abstract and the later review both present elastic collisions as the core mechanism by which a far-out ring can persist, where ordinary theory expects rapid growth into satellites. Even so, the current explanation is not presented as fully complete. The review stresses that greater elasticity alone is not enough unless the particles also maintain a high enough velocity dispersion. Velocity dispersion means the spread of relative speeds among the particles in the ring. If that spread becomes too small, even elastic rebounds may no longer prevent growth, because the particles meet too gently for their post-impact motion to escape mutual attraction. The same review therefore states that low temperature can resolve the paradox only together with a mechanism that keeps particle motions sufficiently stirred. In this way, the collision model explains why particles do not readily stick, but it also reveals a further requirement: they must continue to collide with enough speed. This nuance matters because it separates immediate contact physics from long-term ring survival. A single elastic collision is easy to imagine. A ring that remains non-accreting over long spans of time is more demanding. The particle population must repeatedly avoid the quiet settling that would otherwise let clumps survive. The Oulu summary makes the same point in practical terms. It reports that very elastic collisions do not lead to gravitational accretion in the simulations. even when the ring lies outside the Roche limit and the particles have normal ice densities. But it also notes that researchers continue to investigate what keeps the rings narrow and dynamically organized. The implication is clear: the cold collision explanation is central, but the complete ring state still depends on the broader orbital environment. Within the boundaries of what is now known, the physics of extreme cold offers the most direct answer to why Quaoar's ring should not exist and yet does. The ring particles are likely not behaving like the softer, more energy-losing particles assumed in simpler models. They may be behaving like much colder icy bodies that strike, rebound, and carry enough motion away from each encounter to remain separate. Observations indicate that the ring persists beyond the classical Roche limit. Simulations and laboratory-based interpretation suggest that unusually elastic icy collisions can block the first steps of permanent clumping. It remains uncertain whether this mechanism alone is sufficient in the long term, but it is the central reason current theory no longer treats accretion outside the Roche limit as automatic in the case of Quaoar. A ring is not defined only by where it sits. It is also defined by how its particles share space. Once the problem of Quaoar's rings is viewed in that collective way, the mystery changes shape. It is no longer only the problem of why particles fail to become a moon. It is also the problem of why they remain crowded into narrow lanes without dispersing into a broad, faint cloud. In ring science, crowding is often described by optical depth, a measure of how much light the material blocks along the line of sight. Published work describes the outer ring as having a tenuous continuous component with a typical width of about 100 kilometers, a normal optical depth of roughly 0.5% to 2%, together with a much denser arc only a few kilometers wide, where the optical depth rises to about 1/4. Those numbers show that Q1R is not uniform in crowding. Most of the ring appears lightly populated when averaged over its broadest component, but some segments are far denser and much narrower. This means the ring cannot be treated as one simple band with one simple internal state. The broad, faint component is easier to spread because its particles already occupy a wider radial range. The dense arc is harder to explain because many particles remain concentrated within a very small width. Recent JWST-based analysis notes that the densest portion of Q1R is seen only in a minority of suitable occultation chords, implying that the strongest crowding occupies only part of the ring's full circumference. The inner ring, Q2R, appears less extreme but still teaches the same lesson. JWST observations detect Q2R clearly on one side of the occultation path but not on the other, and the authors conclude that it too has substantial azimuthal variations. Azimuthal means around the circle of the ring rather than across its width. In simple terms, Q2R is also patchy around its orbit. This matters because it shows that the ring system as a whole is not organized into smooth ribbons of constant density. Both rings contain sectors where particles are more concentrated and sectors where they are less so. Any collisional ring also tends to spread. This is often called viscous spreading, not because the ring is a liquid in the ordinary sense, but because countless collisions exchange energy and angular momentum in a way that gradually widens the ring. Particles in slightly inner orbits move a little faster than particles in slightly outer orbits. Repeated encounters transfer momentum through the disk and nudge material into neighboring orbital lanes. Over time, the natural result is radial diffusion, a slow smearing of the ring across a wider range of distances. The Quaoar literature states this directly. The same ultra-cold elastic collisions that help prevent accretion are also expected to cause viscous spreading, and that spreading must be balanced by some confining influence if the rings are to remain narrow. The dense segments make the problem sharper. In a dilute ring, Particles may remain mostly independent except during occasional collisions. In a denser arc, more particles occupy the same small region. Collisions become more frequent, and self-gravity begins to matter more. Self-gravity is the mutual attraction among the ring particles themselves. A recent review notes that a crowded ring does not become infinitely thin. Instead, it tends to adjust toward a marginally stable state, in which local gravity tries to collapse the material, while random motion and orbital shear oppose that collapse. Quaoar's ring has not been observed at that level of detail, but the same principle shows why a narrow, dense ring must be treated as a collective medium rather than a swarm of isolated grains. This balance between crowding and motion shows why one mechanism alone is not enough. Greater elastic rebound can keep particles from sticking permanently, but if the ring becomes too calm, then even elastic particles may linger close enough for gravity to matter. If the ring becomes too excited, then collisions and diffusion can spread it out too rapidly. The review on ring origin states that preventing accretion around Quaoar requires maintaining a high enough velocity dispersion, meaning a sufficient spread in particle speeds through the action of resonances. The ring must stay stirred enough to avoid moon formation, yet not so unconfined that it spreads away from the narrow lanes that observations actually show. The comparison with Neptune's arcs becomes useful here because Q1R is often described as reminiscent of that kind of inhomogeneous ring. Neptune's arcs are dense sectors embedded in a more diffuse ring, and the review emphasizes that such structures would be destroyed quickly by differential orbital motion unless some confinement mechanism maintained them. The same logic applies to Quaoar's densest sectors. Slight differences in orbital speed naturally shear and smear concentrated material. If dense arcs remain identifiable over years of occultation measurements, then some ongoing process must keep preserving those concentrations against shear and collisional spreading. Seen in this light, ring width is not a passive measurement. A width of a few kilometers for the densest arc, a broader width for the faint continuous component, and variation from chord to chord all describe how the system manages its material. A narrow width indicates successful confinement. A broad width indicates that spreading or incomplete confinement is already at work. Variable width indicates that the answer differs around the orbit itself. Recent JWST work suggests that the inner edge of Q1R may be influenced by Wawatt's 6:1 resonance, and its outer edge by Quaoar's 3:1 spin-orbit resonance. So the observed width may represent a band held between competing boundaries, while collisions continue to redistribute material within it. Quaoar's ring system therefore has to be understood as a collective structure. It contains enough motion to avoid easy accretion, enough crowding to produce narrow, dense sectors, and enough spreading to demand continual confinement. The outer ring is stratified into diffuse and dense components, subject to collisional widening and marked by strong azimuthal inhomogeneity. The inner ring, though fainter, shows that uneven crowding is not unique to one orbital lane. Taken together, these properties show why the mystery cannot be solved by ring location alone. It lies in how many particles share a narrow space over time, how they avoid settling into a moon, and how they also avoid fading into an indistinct haze. Quaoar's rings persist as organized matter only because crowding, spreading, and confinement remain in delicate balance. At the center of the ring system, Quaoar is not best treated as a perfectly smooth sphere, with gravity falling away in an ideal and featureless way. The available measurements instead suggest a body whose shape departs from simple roundness, and that departure matters because gravity follows mass. If the central body is slightly flattened or elongated, then the gravitational field around it also carries that asymmetry. For distant ring particles, even a small asymmetry can become important when it repeats with every rotation of the body. This is why the mystery of Quaoar's rings leads inward to Quaoar itself. The rings do not orbit only a point mass in empty mathematics. They orbit a real rotating world with a specific shape, a specific density, and a gravitational field that is likely more structured than the simplest models assume. Quaoar's own figure therefore becomes part of the explanation for where the rings sit and how they behave. This strongest recent evidence points toward a triaxial body, meaning one whose three main axes differ in length. A detailed light curve and thermal study reports that the best fit is a triaxial ellipsoid with a volume equivalent diameter of about 1,090 kilometers and axis ratios of about 1.19 and 1.16. The same study finds that Quaoar's density likely falls between about 1.67 and 1.77 grams per cubic centimeter. Those values describe a body that is substantial, mixed in composition, and not shaped like a perfect rotational spheroid. They also imply that Quaoar's gravity is not fully captured by a single number for mass alone. Its size sets the broad scale of the system, but its asymmetry helps shape the finer structure of the space around it. The evidence for that non-spherical form comes from more than one kind of observation. The same modelling study reports that the visible light curve favours an asymmetric double-peaked variation with a period of about 17.76 hours, while also recovering the previously known single-peaked signal near 8.88 hours. A double-peaked light curve is important because it usually indicates that the body is not axisymmetric. As Quaoar rotates, different projected cross-sections come into view, and the brightness varies accordingly. The study states plainly that such a signal is a strong indication of a non-axisymmetric body, usually interpreted as a triaxial ellipsoid. It also notes that the figure seen in the 2011 and 2022 occultations differs enough to argue against a merely oblate, non-triaxial shape. In simple terms, Quaoar does not present the same outline at all viewing geometries because it is likely elongated as well as flattened. Occultation measurements add a more immediate geometric view. The 2022 occultation fit gives Quaoar an apparent elliptical limb with a measured apparent oblateness of about 0.12. Apparent oblateness means the body looks flattened in projection on the sky, though the true three-dimensional flattening depends on viewing angle and pole orientation. That same analysis notes that the position angle of the ring and the main body are probably close, though not perfectly identical in the measurements available. This matters because the ring plane is expected to respond to Quaoar's gravity field if the body is oblate, or more generally if its gravity has a dominant equatorial symmetry. Then orbiting material tends to settle toward the equatorial plane over time. The body's shape is therefore not just a geometric curiosity. It defines the preferred plane toward which the ring system is likely damped. This connection between shape and ring behavior appears directly in the recent JWST analysis. That work notes that, in the presence of an oblate gravitational field like Quaoar's, a ring tends to damp to the equatorial plane. It also states that Q2R may be coupled more strongly to Quaoar's oblate field, while Q1R may be more strongly perturbed by Waywat's resonance. The contrast is useful. Close to the body, Quaoar's own gravity field is expected to matter more strongly. Farther out, the moon and resonant structure can become more influential. This means Quaoar's shape does not affect every part of the ring system equally, yet it remains central to the local dynamical environment. The central body is not merely the source of gravity in a general sense. Its exact figure helps decide which orbital planes and resonant locations are favoured nearby. Quaoar's elongation also strengthens the importance of the spin-orbit resonance discussed earlier. The JWST analysis states that visible and thermal light curve measurements suggest that Quaoar may be substantially elongated, with a dimensionless elongation parameter of about 0.2, making the 3-to-1 spin-orbit resonance a source of strong dynamical interactions. It further suggests that this resonance is likely to affect the outer edge of Q1R. That statement ties the ring directly to the rotating shape of the body. If Quaoar were close to perfectly spherical, its rotation would generate much weaker periodic forcing on nearby particles. Because it is likely elongated, the rotating asymmetry becomes a real dynamical agent. The ring then feels not just gravity from a central mass, but gravity from a rotating non-round mass distribution, whose repeating pattern can select preferred orbital distances. Even so, the gravitational field of Quaoar is not yet known in full detail. Recent authors stress that models including higher-order gravitational harmonics remain insufficiently explored. A harmonic, in this setting, is one mathematical component of how gravity departs from the simple field of a perfect sphere. The lowest terms describe flattening and broad elongation. Higher terms describe finer irregularities in how mass is arranged. For a small distant body like Quaoar, those details are difficult to measure directly, yet they can matter for narrow rings, because even weak periodic terms may influence precession, confinement, and the exact strength of resonances. The JWST study notes that simplified theoretical models provide only partial guidance, and that models incorporating particle collisions, self-gravity, and higher-order harmonics have not yet been fully explored for Quaoar. This is one of the main limits on current explanation. The body's gravity is clearly not featureless, but it is not yet mapped finely enough to close the problem. The uncertainty extends to spin orientation as well. The light curve study shows that allowed pole solutions depend on assumptions about Quaoar's true oblateness, and the authors discuss a range of compatible pole positions rather than one final geometry. That uncertainty matters because ring dynamics depend on orientation. A slightly different pole changes how the equatorial plane is projected, how the resonance geometry is interpreted, and how well the body's shape aligns with the observed rings. The central body therefore remains partly measured and partly inferred. Its broad properties are becoming clearer, but the exact gravity field available to ring particles is still not known with the precision that would make all dynamical questions simple. In this inward view, Quaoar appears as a moderately dense, probably triaxial icy rocky world whose rotation and asymmetry shape the gravitational landscape around it. Its likely elongation helps make the 3-to-1 spin-orbit resonance dynamically important. Its oblate component tends to define the equatorial plane toward which ring material damps. Its incomplete gravity map leaves room for uncertainty in exactly how the rings are confined and why they remain structured. The rings therefore reflect not only their own particles, but the deeper fact that the body they orbit is not perfectly round, not dynamically simple, and not yet fully known in all the ways that matter most. At the surface of Quaoar, the mystery of the ring system meets the visible skin of the dwarf planet itself. This outer layer is thin in depth compared with the size of the body, yet it is the layer that sunlight, charged particles, and impacts continually modify. It is also the layer from which astronomers recover most of what can presently be known about Quaoar's composition. Spectra show that the surface is not a simple sheet of one ice. It is a mixed and processed crust, with water ice, methane-related compounds, carbon-bearing ices, and dark complex organics all contributing to the reflected light. The surface therefore appears as both a record of long exposure and a sign that renewal has not fully ceased. The strongest and clearest surface signature is water ice. Quaoar has long been known as one of the larger Kuiper Belt objects with pronounced water ice absorptions. and the more recent James Webb Space Telescope spectra confirm that these features remain among the most obvious in its reflected light. The shape of the bands near 1.5 and 2 micrometers is consistent with relatively pure water ice, and the feature near 1.65 micrometers indicates crystalline water ice, rather than only amorphous ice. Crystalline ice is important because it implies that the ice has at some time been warmed or reprocessed. In the outer solar system, energetic irradiation tends to damage crystalline structure over time, so its continued presence suggests that the surface has not remained chemically and physically untouched for the entire age of the solar system. That older inference of renewal remains one of the most interesting surface clues. The 2004 Nature study reported crystalline water ice together with ammonia hydrate, and argued that both should be destroyed by irradiation over long timescales unless fresh material is exposed or emplaced. The authors therefore concluded that Quaoar's surface had been resurfaced relatively recently, either by impact exposure of buried ice, by cryovolcanic outgassing, or by some combination of both. More recent JWST data do not confirm specific features of ammonia-related materials with the same confidence. Instead, the newer study reports no specific spectral signatures attributed to ammonia-related compounds in Quaoar's JWST spectra. This leaves the surface picture more cautious than before. Water ice remains secure. Surface renewal remains a reasonable inference. The exact role of ammonia at the surface is now less certain than early work once suggested. Alongside water ice, Quaoar also shows a smaller but important inventory of methane and ethane. The medium-resolution JWST spectra reveal several absorption bands consistent with methane and several others consistent with ethane. The band positions match pure methane and pure ethane rather than those species dissolved in nitrogen ice. That detail matters because it distinguishes Quaoar from more nitrogen-rich volatile worlds. The surface does not appear to be dominated by nitrogen ice in the way that Pluto or Triton can be. Instead, Quaoar seems to carry a more limited volatile inventory, with methane present in relatively modest amounts, and ethane appearing as one of its most important irradiation products. These light hydrocarbons also reveal active chemistry at the surface. Ethane is not usually treated as a primordial surface blanket on bodies like Quaoar. It is more naturally interpreted as the product of methane that has been altered by irradiation. The same JWST study states that the suite of light hydrocarbons and complex organics is interpreted as the product of irradiation of methane. This means the surface is not chemically still. Weak sunlight and energetic particles gradually change exposed methane into heavier hydrocarbons and then, with continued processing, into darker and more complex carbon-rich material. The red colour long associated with Quaoar fits this picture well. A red spectral slope in the visible and near-infrared usually indicates such irradiation products and complex organics, often grouped under the broad name tholins or tholin-like materials. Quaoar's outer skin is therefore both icy and chemically aged, bright in some bands from exposed ice and reddened overall by prolonged processing. The continued existence of methane-related products carries another implication. The JWST study concludes that the continued presence of light hydrocarbons implies a resupply of methane to the surface. In simple terms, if methane were exposed once and then left to irradiation for a very long time without renewal, the immediate byproducts would eventually be processed onward as well. Their persistence therefore suggests that fresh methane reaches the surface often enough to keep the chain of products supplied. The authors go further and suggest that bodies such as Quaoar may have undergone internal melting and geochemical evolution, but at the surface level the key point is narrower. Quaoar's outer skin does not look like a completely exhausted chemical residue. It looks like a surface that is still being refreshed, however slowly, by access to methane that has not yet been fully processed. Other identified or possible species add nuance to that picture. JWST data indicate a weak carbon dioxide ice feature, likely from very fine-grained frost in low abundance. The same spectra also show a strong absorption, near 3.19 micrometers, that may be due to hydrogen cyanide, though the study notes that this identification is problematic because another expected hydrogen cyanide band is not seen. A possible carbon monoxide feature is also discussed, but only tentatively, with noise preventing a secure detection. These cases show the current limit of knowledge. Quaoar's surface is chemically rich enough to produce subtle features beyond water ice and methane chemistry, but not every feature is identified with confidence. Some materials remain plausible rather than secure. At the same time, several expected species are notably absent or at least not convincingly detected in the present data. The JWST spectra show no evidence for methanol features, no specific nitrogen ice absorptions, and no specific ammonia-related signatures. This absence is important because it helps define Quaoar's surface as an intermediate case among large trans-Neptunian bodies. It is icy and chemically evolved, but not obviously coated in abundant supervolatile nitrogen. It retains methane-related chemistry, but more weakly than the largest methane-rich dwarf planets. It preserves crystalline water ice, yet it does not presently show the full volatile suite seen on Pluto-like worlds. In that sense, the surface seems to belong to a body that has kept some volatiles, lost others, and undergone long chemical processing under outer solar system conditions. This surface composition also matters for the rings because it hints at what loose material around Quaoar may be made of. If the outer surface contains water ice, methane-related frosts, complex organics, and other irradiated products, then particles derived from that surface by impacts or other slow renewal processes would likely reflect some part of that same composition. The connection cannot yet be stated in detail, because the ring particles are not directly sampled spectroscopically with the same precision. Even so, the surface gives the best present guide to the material reservoir available near Quaoar. It suggests a body whose outermost layers are icy but processed, cold but not chemically inert, and old yet not wholly static. The surface keeps the marks of irradiation, but it also keeps signs that fresh material still reaches the light. Beneath Quaoar's processed surface, the body is large enough to raise a deeper planetary question. It is not only an icy object with a ring system, it is also a world whose hidden interior likely controls much of what happens outside it. Density estimates near 1.75 grams per cubic centimeter place Quaoar in the range of a mixed ice and rock body, rather than a nearly pure ice sphere. Recent dynamical work on the Quaoar-Weywatt system goes further. Under the assumption that the rings lie in Quaoar's equatorial plane, the detected dynamical obliteness is low enough to imply a differentiated interior, meaning that the body is likely internally separated into layers rather than uniformly mixed throughout. A differentiated body is one that has been warm enough inside for denser material to move inward and lighter material to remain higher. In practical terms, that points toward an early period of internal heating. The JWST surface study argues that Quaoar, together with a few similar mid-sized dwarf planets, is large enough to have undergone internal melting, differentiation, and geochemical evolution. The same study connects the present surface hydrocarbons to a continuing resupply of methane, and suggests that this methane reservoir may itself derive from internal geochemical processing. That does not prove a present liquid layer inside Quaoar, and it does not reveal the exact arrangement of core, mantle, and crust. It does, however, place Quaoar among the outer solar system bodies whose present surfaces may still carry the chemical consequences of ancient interior activity. The interior matters to the rings because gravity depends on structure, not only on total mass. A body with a differentiated interior, non-spherical figure, and evolving surface brightness does not present a perfectly simple, gravitational environment to nearby particles. The recent orbital analysis of Quaoar finds that a purely Keplerian model is insufficient and requires Quaoar's non-spherical gravitational field to be included. That same work also detects centre-of-body and centre-of-light offsets, likely caused by latitudinal albedo variations on the surface. Together, these results show that the hidden interior and the visible surface both affect how the system is modelled. Quaoar's rings therefore orbit a layered and imperfectly symmetric body whose internal state leaves measurable traces in the motions around it. Even with this progress, the interior is still not known in full. The likely differentiation is inferred rather than directly seen. The dynamical oblateness is detected only at modest significance, and it depends on the assumption that the rings trace the equatorial plane. The light curve and occultation results constrain shape and density, yet they do not deliver a complete map of the gravity harmonics that would fully specify how mass is arranged inside the body. Observations indicate enough to show that Quaoar is not a simple frozen lump. It remains uncertain exactly how strong its internal layering is, how completely rock and ice separated in its past, and how much of that ancient structure still influences the body today. This uncertainty leads directly into the unresolved origin of the rings. The survival problem is now clearer than when the rings were first reported. Very cold. Highly elastic collisions can help prevent rapid accretion, and resonances with Quaoar's rotation and Quaoar's orbit may help confine the material into narrow orbital lanes. Yet these mechanisms explain how a ring can persist more readily than they explain how the ring begins. The Broad Ring Review published in 2024 states that Quaoar's rings remain an additional surprise because they orbit well beyond the Roche limit, and it frames their origins and evolution as an open problem rather than a settled one. One class of ideas treats the rings as debris from a collisional event. An impact onto Quaoar, or the disruption of a small satellite, could in principle produce a disk of fragments around the body. That disk would then need to evolve under collisions, resonances, and spreading into the narrower structures now observed. Such a scenario is attractive because it gives the rings a clear material source. At the same time, it is not yet demonstrated in detail for Quaoar's present ring architecture. Any successful collisional model must explain not only how debris is launched into orbit, but why it ends up concentrated in the observed ring zones, why both known rings remain beyond the classical Roche limit, and why the outer ring contains dense arcs instead of a smooth band. A related and now more specific possibility is that the rings are the remaining part of a formerly broader collisional disk. That idea gained support from a 2025 study reporting a previously undiscovered small satellite around Quaoar from occultation data. The authors find that this object likely orbits near a resonance with the outer known ring, and state that the discovery provides evidence that the rings may have been part of an initially broad collisional disk that has evolved considerably since formation. This is an important clue, but it is not yet a final solution. The newly reported satellite remains difficult to recover directly, and its long-term role in the ring system still requires further observation and modelling. Other possibilities remain more indirect. The rings could be fed or renewed by material excavated from Quaoar's surface, or by gradual loss from small orbiting bodies, but present observations do not yet isolate a specific active source. The recent JWST occultation study places a strong upper limit on any global methane atmosphere and concludes that atmospheric processes are not the source of Quaoar's light hydrocarbons. That result removes one possible route for broad atmospheric transport. Yet it does not determine the source of the solid ring particles themselves. It simply narrows the problem. At the innermost level, the mystery resolves into an incomplete picture. Quaoar appears to be a layered dwarf planet with substantial rock, likely internal differentiation, and a history of melting and geochemical change. Its rotating non-spherical gravity field helps shape the resonant landscape in which the rings survive. Yet the origin of the rings remains unsettled. Observations indicate what the rings are doing now with increasing clarity. It remains uncertain exactly when the ring material first enters orbit, whether it comes from impact debris, a disrupted moon, or a broader ancestral disk, and how that original material is narrowed into the strange cold bands now seen around Quaoar. The deepest layer of the story therefore remains the most hidden one. The interior gives the system its conditions. But the first beginning of the rings is still only partly revealed. Quaoar remains in the dark outer reaches of the solar system, turning slowly beneath weak sunlight. Around it, the rings continue their narrow paths, light and cold and improbable in the old classical picture. The dwarf planet holds its quiet shape, its surface carrying water ice, processed hydrocarbons, and the marks of long exposure to space. Beneath that surface, a deeper structure likely endures, layered and ancient, preserving the record of internal change that can no longer be seen directly. The rings do not offer a simple ending. They remain a measured fact and a partial explanation at the same time. Their distances are known, their narrow lanes are known, their uneven density is known, their survival beyond the classical Roche limit is known. Yet the full path from origin to present state is still incomplete. Observations show where the particles are. Simulations show how extreme cold may help them rebound rather than grow. Orbital analysis shows that repeated gravitational rhythms may help confine them. Even so, the whole system keeps some part of its silence. This is often how the far solar system appears when it is studied with care. It does not refuse understanding, but it yields it slowly. A small world at great distance can carry enough structure to test an old rule about rings and moons. A faint dip in starlight can reveal a band of orbiting matter where theory once expects none. A cold object beyond Neptune can remain both orderly and unresolved. So Quaoar continues around the Sun, and its rings continue around Quaoar, each motion steady within a darkness that changes very little from day to day. The mystery does not become less real because part of it is now explained. It becomes quieter, more precise, and more deeply set into the natural order of the outer solar system, where even a narrow ring of ice can remind science that distance, cold, and time still keep their own subtle laws.